The first glue wasn't born in a lab. It was Neanderthal birch tar, and it set off a chain of adhesive science that ends with gecko feet and spacecraft grips. When most people picture scientific breakthroughs, they imagine laboratories, gleaming instruments, and researchers in white coats. The history of adhesives tells a far older story, one that begins not in any facility, but around a prehistoric fire, with a Neanderthal gripping a strip of birch bark. Experimental archaeology by researchers at Leiden University established that our evolutionary relatives were already producing birch bark tar as early as 200,000 years ago, making them the first chemists in recorded history to engineer a synthetic material from raw, natural ingredients. Scientists demonstrated at least 3 distinct methods for extracting tar from birch bark, ranging from condensing smoke over heated bark to submerging bark rolls in carefully managed embers. Each approach demanded controlled heat and precise timing, essentially early process chemistry. The resulting black, viscous substance was used to haft stone blades onto wooden handles, repair broken pottery, and waterproof canoes. It was a glue, a sealant, and a construction tool in one, history's first documented multipurpose adhesive. A 2026 finding published in PLOS 1 revealed that birch tar is measurably effective against Staphylococcus aureus, the bacterium behind a wide range of human skin infections. Applying a binding agent that also fought pathogens was, in retrospect, an accidental masterstroke of material ingenuity that modern researchers are only beginning to fully appreciate. All adhesives rely on 2 distinct types of forces working simultaneously. Adhesive bonds form between the adhesive's own molecules and those of the surface it touches, a molecular handshake across material boundaries. Cohesive bonds hold the adhesive together internally, giving it structural integrity so it does not simply pull apart from within. Most commercial glues consist of adhesive polymers dissolved in a solvent that keeps them fluid until they are needed. That sharp chemical smell, familiar to anyone who has opened a tube of glue, comes from the solvent evaporating on contact with air. Natural adhesive molecules served this purpose long before synthetic chemistry existed. Vegetable starch dextrin, the milk protein casein, and terpenes extracted from tree resin all held human civilization together for thousands of years before a single synthetic formula was ever developed. 2-component adhesives trigger a chemical reaction when their separate components are mixed together. That reaction generates an entirely new molecular architecture, engineered with a specific mechanical performance in mind. Once these glues cure, the bonds are essentially irreversible. Breaking a surface after it has fully set destroys the joint permanently. Tape seems to violate intuition. Press it against a surface and it holds. Peel it away and it releases cleanly. No solvent evaporates. No chemical reaction occurs. The secret lies in one of physics' most underappreciated phenomena: van der Waals forces. Van der Waals forces are weak, attractive interactions that arise between any 2 materials when they get close enough together, closer than the naked eye can detect. The asymmetric orbit of electrons around atomic nuclei creates fleeting positive and negative zones within molecules, and those tiny charge imbalances attract each other across vanishingly small gaps. When tape is pressed onto a surface, its soft, viscoelastic adhesive flows into the microscopic cracks and grooves of whatever it contacts. This dramatically increases the actual area of contact, bringing adhesive molecules close enough to experience van der Waals attraction and lock the tape in place. Nature worked this out long before engineers did. Research confirmed that the roughly 500,000 keratin hairs covering a single gecko toe, each tipped with hundreds of nanoscale projections called spatulae, generate adhesion entirely through van der Waals forces, with no glue involved at all. A single gecko foot exerts approximately 10 newtons of force across just 100 square millimeters of surface. Ask which adhesive is strongest, and the answer is, frustratingly, it depends. Tensile strength measures resistance to being pulled straight apart, and by this metric, cyanoacrylate, commonly known as superglue, is genuinely formidable. Industrial-grade cyanoacrylates achieve tensile strengths of up to 4,000 pounds per square inch on metal substrates. To make that concrete, a single square inch of properly cured superglue could theoretically bear the weight of 2 full tons. The polymerization that produces this bond is triggered by moisture already present in the air, meaning the glue cures without any mixing or added catalyst. Shear strength, resistance to forces that slide bonded surfaces past each other laterally, matters enormously in structural applications, as does resistance to heat. Specialized aerospace epoxies maintain structural integrity at temperatures up to 500 degrees Fahrenheit, while standard superglue bonds begin to fail around 180 degrees Fahrenheit. That temperature gap is not trivial. The choice of adhesive in a jet engine component, a heat shield, or an exhaust manifold is an engineering calculation treated as a genuine safety matter, one where the wrong answer can have catastrophic consequences. Gap-filling capacity introduces yet another variable. Cyanoacrylate requires surfaces to be essentially flush, failing across gaps wider than roughly half a millimeter. In field emergencies, with irregular surfaces, even duct tape earns its legendary reputation. On the Apollo 17 mission, astronauts used strips of duct tape to repair a broken fender on the lunar rover on the Moon's surface in 1972. Following the 2002 discovery that gecko adhesion is mediated entirely by van der Waals forces, requiring no glue, no moisture, no chemical reaction, researchers worldwide raced to replicate the mechanism artificially. Scientists at Nanyang Technological University in Singapore developed a smart adhesive using shape memory polymers that is more than 10 times stronger than a gecko's natural foot adhesion. By heating that material gently, users can switch it from fully bonded to freely detachable in seconds, a reversibility no conventional glue can offer. This capability opens new possibilities for robotic grippers, reusable fasteners, and surgical tools that must bond and release on demand. NASA has taken this principle into orbit. The agency's Astro-B robots, tested aboard the International Space Station, now use gecko-inspired grippers capable of grabbing and releasing surfaces in complete vacuum, with no adhesive compounds at all. Liquid glues simply cannot function in zero gravity. Solvents cannot evaporate in a vacuum. Uncured adhesive floats freely in pressurized cabins, and outgassing of volatile compounds can contaminate precision optical instruments. All liquid adhesive requirements in space are currently handled by pressure-sensitive tapes that must pass strict low-outgassing protocols before being cleared for any mission. The oldest adhesive technology and the newest are, in a surprising way, converging. Neanderthals built tools using mechanically applied bonding agents that required no mixing and left no residue. Modern spacecraft engineers are arriving at the same conclusion, that the most sophisticated grip sometimes relies not on elaborate chemistry, but on the quiet, invisible attraction of molecules that are simply very, very close together.